Hello. So today we're going to talk about a circuit, an experiment that's inside this 60-in-1 science fair electronic project lab from the good old days of RadioShack when there were brick and mortar electronic stores all over the place. They are long gone now, but we still have those. So, radio station. That's the circuit. So I'm just showing you the circuit in that book, but I'm going to switch to LT Spice. Okay, I'm back in LT Spice, and this is exactly the circuit that was in that booklet from RadioShack. So it's a radio station, AM transmitter, in other words. Let me see. So this is a transistor. You can use any NPN. It's used as a Class C amplifier to maintain the oscillation in that LC tank here. That's your LC tank. Okay, so that's your oscillator. And I did a video about just the oscillator part of this, which is very similar. So it's basically just the oscillator. So I'll put a link right now. So here you have an increased difficulty because now you have also a audio signal being fed to the circuit, and it's actually being fed at the base. So this is the base, and that's your audio frequency signal. Here it's just a sine wave. So it's fed at the base. Usually AM transmitter like this part, the audio frequency signal, is fed probably in the collector, somewhere in the collector. You get the amplitude modulation by varying the supply, the voltage supply to the collector. But here it's different, and that's what makes this circuit a little bit interesting. So what's interesting about this circuit is that, as I said, you have the audio frequency being fed, injected at the base, and you also have an oscillator within that circuit. So that makes it pretty cool. And very few components, less than 10, I guess, fewer than 10. Okay, so let's run it. Let's run this thing and see what happens. So 10 milliseconds I chose. I don't know why. Just so that you can see the audio frequency signal, the envelope. So let's look at VB, the voltage at the base, and try to understand why it looks that way. Okay, so this is VB. So basically you have your radio frequency signal coming from the oscillator. I mean, if I zoom, you can see it better, but it's just a very high frequency signal. And here you have your modulated signal. So why do we get this? Why do we get this? Let's see if I can explain why it looks like that. I'm gonna have to switch to whiteboard. Okay, so I'm back with my whiteboard, and let's plot VB. So it looks like that. So let's put the 0 line. Let's put the 0.6 or 0.7, 0.6, the cutoff point basically. And it basically oscillates, the audio signal shows up here. And it's bit about, so this is -4 and -4.6, something like that, 4.6. And of course you have the radio frequency signal going like this. Of course, this doesn't, I mean, it's not there. It's like, okay, but you get, so it's, so first let's explain why another whiteboard. I'll get back to that one. Okay. I mean, usually, if you look at just a regular oscillator, it would look like this. You would have the 0.6 volt, the 0 volt, and you would have, so that would be your bias, which is pushed down, okay, way down, so it's a class C. So that would be a regular oscillator. And I made a video about this, and I'll give a link. And your oscillator, I mean, it's gonna go like up and down like this, centered on that bias value for the voltage. But when you have an oscillator, you don't get this. When it's operating like this, it's gonna be flat here. And when this is flat, so here it's the transistor is off pretty much all the time. Every time you under here, the transistor is off. So the transistor is only on if you are above that line, the 0.6, the cutoff line. And here you don't get the top of the sine wave, because here you are going into saturation. And you can look to make sure you can see that VCE equals 0 when you get here. So you go straight from cutoff to saturation, and that gives the impulse. That gives the impulse to that LC tank to maintain the oscillations. So in this case, the transistor is not really used as an amplifier of the signal. You don't get an amplification of the signal. You get amplification of the power through the impulses. So here you got the impulses that are fed back into the LC tank, and that's how you maintain the oscillation. So that explains this part. Okay, so at those basically flat tops, you have VC equals 0, so you go into saturation. So that explains that. How do you explain the audio frequency sine wave at the bottom? Well, okay, I think I'm gonna have to have another one. Okay, so another whiteboard. So this is the typical case. You have a flat bias. So it's a horizontal line, and which averages the swings. So this value is the average of the swings. In our case, the bias is controlled by the audio frequency signal. So the bias is not a straight line. It's whatever. I'm going to put it higher. Hold on. I'm going to put it here. So this is your audio frequency signal, and that's actually your bias. So the AF is equal to the bias. So instead of being horizontal, it's now a sine wave. And where is your radio frequency signal? It's in between. It's gonna be here. So the bias is still the average of the swings, but now it's modulating. So it's not straight, it's following the audio frequency signal. This is what you see in that signal. So the bias is probably somewhere here. Okay, so that's why you get this at the bottom. You get your, so this is the amplitude modulation. So if I go back to that LT Spice simulation, so this is your audio frequency signal, sine wave. This is a sine wave, 10 volt amplitude, 1K frequency. And it's going into the base. So it's basically acting on the DC bias, and it makes it a sine wave. So it's probably sitting around here. So this is your bias as a sine wave, and that's why you get this at the bottom. Now what would be interesting to see is the VC, which is here. Okay, so this is VC. It went through a change of sign, but it is in phase with the bottom. So that's your VC. So you still have the modulation here. It's in phase with that VB. So VC is in phase with VB. So why is that? It's because you are using a common emitter amplifier. You're using an LC tank with a tap. And I made a video about this, about why you end up in phase. So I'll put a link to that video right now. But I can briefly explain why. Okay, so yeah, I had a mishap. I forgot to record. So I'm gonna have to go back to that explanation without having to redraw everything, which is good. So yeah, so when you have the common emitter amplifier, which is shown here, so you have the voltage divider, bias, base emitter, collector of your NPN transistor, RE, RC. So that's your common emitter amplifier. So that would be your input, and that would be your output. Input sine wave like this, and it gets amplified, and you have a 180-degree phase inversion. So that's one 180-degree phase inversion. Actually, you can explain it here pretty easily. So we know that IC is equal to beta IB. So you know that your transistor is a current source. So IC equal beta IB. It doesn't depend on RC. It doesn't depend on RE. It depends only on IB and beta. So current source. Then the VC, which is the voltage at the collector, is equal to VCC. This is the output, by the way. This is the output. The output is here at the collector. So VC is equal to VCC minus the voltage drop RC. So then the voltage drop is RC times IC. So that minus sign causes that 180-degree inversion. So that's why you go from this to that, from positive swing to negative swing. So that's one inversion. There's another inversion because of the LC tank and the way it's tapped. So you have a tap which goes to ground here, but it could go also to a positive supply. And you have a V top and a V bottom. And if you plot those two, so this is your V top and this is your V bottom. Just by the fact that you have a center and a center tap in this case. But you don't have to be at the center, you could be at lower. So that's your second inversion. So you have two inversions in you have two inversions in this case. That's why you end up with a 360-degree inversion or zero inversion. So that's why the two signals are in phase. And now I can go back. Okay, so back into LT Spice. Okay, so we looked at VB, so this VB in green, VC in blue, and of course your output, I mean you would put like a antenna here, so you would have an R out here, which is the load basically. So that's your circuit. Very interesting circuit, very few components, so it does work. I tried it. I actually built it in my little experiment lab. It works pretty good. It's not super good because you don't have much. The percentage of modulation is not very good. So I'm sure there are better circuits out there. So I think I'm going to stop here. But before I go, I would like to show you a website that's pretty cool. Yeah, so this is a website that I found is very cool. It has tons of free PDFs of magazines, electronics magazine, but not just electronics, huh? There's lots of stuff. Electronics magazines, books, technical books. And usually what I look at, when I look at is I go into technical and engineering, and I mean, you can look into this one, the modern era. So this is consumer electronics modern era. And there's also the hobbyist publications modern era. So modern era, I mean, it could still be from the 60s or 70s. But a lot of those books are from the 30s and 40s. So it's going to be about 1,000 tubes. I mean, it's still interesting because the tubes kind of behave like transistors, but it's probably better to just look at transistors. But yeah, you could spend a lot of time here on this website looking and looking and looking. I don't particularly recommend looking at magazines because usually the circuits described there are not well explained and they are pretty difficult to understand. I recommend just looking at the books. And in there you can find the RadioShack, the famous engineers mini notebooks from RadioShack that were pretty popular back in the day. But yeah, this website is incredible. You can find a lot of stuff, but you can also, it's like a rabbit hole. You may have to go through a lot of books to find one that looks okay for you. Okay, anyway, please like, comment, subscribe. That helps the channel, and I will make more videos. Okay, see you. Bye.